Welcome to today's Explainer. I'm Dr. Chem, and I am absolutely thrilled to invite you inside our analytical laboratory today. Just take a look around at all this. We're surrounded by precision balances, high-tech digital sensors, and beautifully illuminated glassware. And we're setting up all this equipment today to immerse ourselves in a fundamental property that literally dictates the architecture of our entire physical world. We're talking about density.
It's kind of the ultimate captivating mystery, right? Think about it. If you drop a massive iron anchor into the ocean, it plunges straight to the dark floor below without a second's hesitation. But if you release an air bubble underwater, it races right back up to the surface. Or think about a helium balloon effortlessly floating away into the sky. So what exactly are the unseen mechanics at play here? Why do some materials rise while others just fall? Well, the answer lies entirely in how tightly packed the matter inside them actually is.
Okay, let's dive right into the core principle here. The fundamental equation that unlocks this entire phenomenon is incredibly elegant and, honestly, pretty simple. It's just mass divided by volume equals density. That's it. That's the golden rule.
So to put that into everyday terms, density is a physical quantity that describes the exact amount of mass per unit volume. Imagine zooming way into the microscopic level. We are looking at the molecular arrangement, the actual spacing of the particles. The closer and more tightly bound those microscopic particles are to one another, the heavier the object is going to be for its size. That compact spacing is precisely what gives an object its density, and it entirely dictates how fluids and solids are going to interact.
Let's actually watch this in action through a wonderfully precise laboratory procedure. We always start by placing a pristine empty pycnometer, which is just a highly specialized glass flask, onto a sensitive digital balance so we can record its mass. Next, we carefully pour in a known volume of our liquid. Maybe it's ethanol or glycerol, and we just watch those descending droplets settle perfectly into the glass. Then we weigh the whole thing again. By subtracting the weight of the empty glass, we isolate the exact mass of our liquid. Finally, we just take that mass and divide it by our volume. Let's run the numbers because the math here is beautifully clean when you use absolute clinical precision. Say our empty glassware is exactly 50 grams. After pouring the liquid, our total mass bumps up to 60 grams. Our volume? 10 milliliters. Subtracting 50 from 60 means we have exactly 10 grams of liquid sitting in that flask. 10 grams divided by 10 milliliters gives us a final density of exactly 1 gram per milliliter. Just perfect.
Now imagine taking this math and applying it to create something visually stunning, a density tower. If we carefully pour different liquids into a tall glass jar, one by one, something amazing happens. Because they have vastly different particle structures, they actually don't mix, they stack. The densest liquid, thick golden honey, sinks right to the bottom. Above that sits corn syrup, then pure maple syrup, a distinct white layer of milk, some green liquid soap, clear water, yellow vegetable oil, and finally, floating effortlessly at the very top, rubbing alcohol. It creates this perfect, colorful column separated entirely by compactness.
But here's the really fascinating part. These values aren't static. Density varies not just by the type of liquid, but also by temperature. As a liquid warms up, its particles actually spread out, which lowers its overall density. And this dynamic is absolutely crucial in fields like medicine. For pharmaceutical scientists, calculating the exact density at specific temperatures is a matter of life and death when preparing solutions, determining the safe concentration of medical fluids, and ensuring strict quality control.
You know, our modern analytical chemistry actually traces its roots all the way back to the 3rd century BC. We owe a huge debt to the Greek philosopher Archimedes. Archimedes' principle states that any solid suspended in a fluid is buoyed, meaning it's pushed upward, by a force exactly equal to the weight of the fluid it displaces. It is the fundamental law of fluid displacement, and it's the exact reason why a massive steel ship can float while a tiny little pebble sinks to the bottom.
And that brings us to one of my absolute favorite pieces of laboratory equipment, the hydrometer. Picture a sealed, hollow glass tube. At the wider bottom portion, there's a ballast, often made of lead or mercury, just to keep it stable and upright. Rising up from that base is a narrow stem marked with delicate, precise graduations. When you gently lower this instrument into a tall cylinder of liquid, it just floats freely. The exact point where the liquid surface touches that stem, that gives you a direct, instant reading of its relative density.
Because harnessing buoyancy is so universally useful, scientists have actually created highly specialized hydrometers for totally different industries. We have a lactometer to measure the fat content and purity of milk. Brewers rely on a saccharometer to measure dissolved sugar. An alcoholometer? Well, that tests the strength of spirits. In medicine, doctors can use a uranometer to quickly assess a patient's hydration levels. And in heavy industry, a thermohydrometer tests petroleum density while simultaneously compensating for those temperature changes we talked about earlier.
This brilliantly illustrates how a simple glass instrument acts as a highly sensitive physical sensor. If you place a hydrometer in a low-density liquid, say pure ethanol, it sinks much deeper into the fluid. Why? Because it has to displace a lot more liquid to support its own weight. But if you place it in a high-density liquid like thick brine or milk, it floats much higher near the surface. It reacts visibly and instantly to its chemical environment.
Section 1. Hydrostatic weighing, the ultimate density test.
So how do we push this even further? By comparing the normal weight of an object in the air against its apparent reduced weight when it's fully submerged in liquid, we can calculate its precise relative density. The liquid literally pushes back with a buoyant force, and measuring that specific difference reveals exactly how much volume the object is displacing.
One of the most fascinating applications of this is actually in human biology. A living person can be weighed underwater to determine their exact body composition. Human fat has a very low density. It increases your buoyancy, making you want to float. Lean muscle, on the other hand, is highly dense and actually increases your underwater weight. By doing the math on that difference, doctors can calculate your precise body fat percentage, though they do have to carefully factor in your residual lung volume. That's the air naturally trapped in your respiratory passages. Because, well, that trapped air acts like a built-in balloon, and we definitely don't want that throwing off the digital calculation.
Section 2. Macro applications, from the lab to the globe.
Let's zoom way out for a second, to the frozen expanses of the Arctic. Sea ice density changes dramatically by season, and that directly impacts how our satellites estimate global ice thickness. To measure this precisely, scientists rely on hydrostatic weighing. But wait, they obviously can't weigh ice in water, it would just melt. So instead, they brilliantly weigh the ice samples in sub-zero kerosene. Kerosene has an even lower density than sea ice, and crucially, it won't melt the sample while they're running the numbers.
And here is the truly incredible part. The exact same mechanics happening in our small glass density tower back in the lab, they are actively driving Earth's massive oceans. Warm, less dense ocean water naturally rises to the surface. Meanwhile, the cooler, much denser salt water sinks rapidly to the ocean depths. This perpetual, massive sinking and rising is literally the engine of ocean circulation. It is the mechanism that regulates our entire global climate.
So from the absolute micro to the massive macro, particle spacing completely shapes our reality. It regulates our climate and ocean currents. It allows satellites to gauge the health of our polar ice caps. In the hospital, it ensures precise, life-saving pharmaceutical dosing. And in heavy industry, hydrostatic weighing is even used to detect dangerous hidden voids inside thick radiation shielding blocks. It's an invisible force, maintaining the quality of everything around us.
We've seen today how a seemingly simple mathematical ratio, just mass divided by volume, can dictate the layers of a cocktail, the fat on our bodies, and the actual climate of our planet. It really leaves you to wonder, doesn't it? If density shapes everything from the life-saving medicine in our veins to the massive currents of our oceans, what other invisible forces are quietly orchestrating the universe around us? Thank you so much for exploring the laboratory with me today. Keep asking questions and keep looking for those hidden mechanics in everything you see.